Welcome everyone. My name is Vivek and I'm an engineering manager at Meta. I support the distribution infrastructure and today we're going to talk about model freshness. What it is, why it's important, the infrastructure investments we've made to improve it, and how we rise to the challenge of building the state-of-the-art recommendation systems. So what is model freshness? In very simple terms, model freshness is the time it takes for recommendation algorithms to understand your interactions or intent, incorporate them, and serve you better, more relevant content. Let me give you an example. Imagine you're watching a football game live at a stadium and there's an exciting moment that takes place, a touchdown or a great run by one of the teams. You want to share that excitement and engage with it. At that moment, being recommended threads or discussions that are relevant will be more interesting. This could be from other folks watching a live stream somewhere else in the world or are present where you are. Sharing that moment can be exciting. And the same recommendation hours later may not be as relevant or exciting anymore. We found that improving the freshness of some models can significantly improve user engagement and experience. Model freshness, in essence, captures how quickly the models can be trained and used for providing better recommendations. As users engage with content, we continuously gather new signals about their interests, what they like, dislike, and the intent they're showing. It is vital to continuously refresh AI models and reflect the most recent signals to maintain fresher models for recommendations through better reels, stories, posts, or ads. Recommendation systems follow a very similar sequence of processing steps. At a very high level, they go through the following stages. Data generation, where the signals that were mentioned are gathered. Training, which is ingesting the signals to train the new versions of the models. Publishing, which is once a model is trained, performing post-processing functions and making the model available for use. Deploying or distribution, which is scaling out the model and deploying it across the fleet ready for inference. Inference is actually using the model to serve recommendation requests. We're going to focus on the stages after training in this session. We're not alone in pursuing freshness. Many other companies are pursuing this goal through different or similar approaches, but here we'll talk about the journey we've had at Meta, the challenges we've faced with our infrastructure, and how we worked through them to develop state-of-the-art recommendation systems over the last couple of years. In the following slides and through the rest of the talk, I'll be joined by Xianzheng Zhang and Lujia Zhang. First, Xianzheng will cover some of the main challenges that we faced in the journey. He'll also cover some of the most notable technical developments that improve freshness. Following him, Lujia will dive deeper into how we achieve state-of-the-art freshness for our systems with streaming. And then we'll take a brief look at how we're going to take this further and cover some of the investments we'll be making in the future. With that, I'll hand off to Xianzheng.
Thanks, Vivek, for the introduction. So, why the problem is so challenging? Firstly, it comes from the scale. At Meta, we have 20,000 models that we serve across millions of containers, or we call them predictors. The model size can be large, ranging from hundreds of gigabytes to terabytes. Furthermore, we have to serve and update these models across tens of data centers across the globe. This incurs a large amount of infra cost, including storage, network, and predictor capacity itself. Secondly, this is not a one-size-fits-all problem. There's a large diversity of model types we use at Meta for recommendation purpose only. Even inside a single model type, there are multiple components that would favor freshness differently. For example, one of the models could behave well if we refresh it every few hours. However, one single component in that model could benefit even further and have better prediction results if we refresh it every minute or even less. So when designing the entire system, we have to take account into such flexibility. So in the end, the model owners can make a proper trade-off between the freshness and the infra cost they have to pay to enable freshness. Another challenge is that the entire model freshness pipeline involves so many complicated infra components. We have to tackle the problem holistically. Otherwise, the slowest component will become the bottleneck. Therefore, we started a multi-year journey to gradually transition each infra component to be more freshness aware. Let's start to look into where we were a few years ago. This is a simplified architectural graph. It's a process called snapshot transition. The training system will continuously train the model with real-time update and real-time data from our other Meta products. Once in a while, the model state will be checkpointed and persisted into storage sources. This is mostly for failure tolerance. However, one of the checkpoints will be selected by another snapshot publishing service every few hours to generate and publish the snapshot. Snapshots are better optimized for the purpose of inference. So they also contain the latest parameters for the model itself. The serving control plane will discover the existence of this new snapshot and notify the predictor across a global data center to gradually load the latest snapshot. The entire process will take 3 to 6 hours, which we refer as training to serving latency in this talk. As you may notice, there are so many low-hanging fruit in this architecture. First of all, we could have the snapshot publishing and checkpoint persistency to happen in parallel, embedded in the training system itself instead of routing across the different publishing services. Secondly, people apply aggressive optimizations to reduce the size of the snapshot without sacrificing the prediction quality. This will help us reduce the storage cost and network distribution cost for those large snapshots. Finally, we adopted a network locality-aware peer-to-peer system to distributing the snapshot to each single predictor across global data centers. The new peer-to-peer system ensures the distribution to be efficient and fast. Together, this gives us a training to server latency at 1 to 2 hours level. How do we even go further? Well, the first observation we make is, can we trade off the model consistency? In the past, the predictor can serve traffic if all the parameters come from the same snapshot variant, either the old one or the new one. They couldn't serve traffic if it is in a mixed state, which is inconsistent. The problem with this approach is, though, we have to introduce capacity buffers. Those buffer predictors will gradually load the newer snapshot, and once the process is done, it will get swapped with another production predictor instance, which is still running with the older snapshot. And the process will continue until all the predictors load the newer snapshot. It can take a long time if we don't have enough capacity buffers, which is almost true anytime. After many experiments and studies, we actually concluded that many recommendation models do not need to be consistently updated. Namely, the predictor can have in-place snapshot update while serving inference request, and this won't affect the inference result much. Extending this idea even further, can we actually have the predictor to stay in this inconsistent state for even longer time? How about we choose those components in the model that are more freshness sensitive and update this component at a higher cadence, like every 10 minutes. For the remaining of the model, how about we update them at a lower cadence, let's say every 1 hour with the snapshot transition. After many more studies, we concluded that this is also doable And it actually brings the benefit of freshness without incurring significant amount of infra cost. With those observations, we apply both delta update and in-place update to the model freshness pipeline. We also further improve the peer-to-peer distribution system to further reduce the network latency for distributing the data to predictors. We also introduce newer component in the serving control plan to discover the existence of snapshot and data faster and notify the predictor about this newer update faster. Together, this gives us a training to serving latency at 10 to 30 minutes. Alright, how can we even actually go further? I will leave this question to Lujia.
Thanks, Xianzheng, for your great talk on how model update works. Building on that, I will talk about how we involve this to a streaming system. From past experience, we have noted two key observations. First, shift to asynchronous components. Operations such as uploading the snapshot file to remote storage, registering metadata can happen in parallel. As soon as a trainer generates new update, we can distribute them directly to predictor servers, no longer waiting for every component to finish before moving on. Secondly, we also reconsider our approach to publish deltas. Let's dive deeper. For each model, there can be thousands or more of weights represented as tensors. A single delta update often contains some of these tensors, and different trainers produce updates in parallel. In the traditional bulk approach, we would wait for all changes across trainers to finish, sometimes taking several minutes to create one complete delta, and then additional time for the predictor server to patch them. This can lead to increasing latency, especially as size increase. The main issue here is we are blocking on all changed tensors to be ready. Instead, we can adopt a streaming approach, where each update piece is published as soon as it becomes available, as illustrated here. By adopting this, we can effectively overlap the latency on training, distribution, and serving. This is a typical pipeline optimization. In short, we transform the previous synchronized bulk update system into a continuous flow of streaming update. Here is an overview of the data flow. The streaming system requires distributing a large amount of data effectively across different data centers. Underneath, we built a new P2P system on top of the system Xianzheng talked about earlier. The system evolves to better support streaming updates, bridges the training host and the serving host, forming what we call a P2P forest. The forest handles model update across Meta global data centers at lower latency. For the ease of discussion, let's simplify the data flow into this higher architectural graph. We have a training system that generates delta updates on the left side. In between, there is a distribution layer, bridges training and serving, distributing the delta updates in real time. On the right side, a serving system deployed across multiple data centers consume distributed delta and apply them to the model that serve traffic. Having established our streaming system, we now encounter new scaling challenges as our model grows larger and more powerful to deliver better ranking results. To accommodate this growth, we must scale up our training and inference infrastructure. Let's take a look at what we have been scaling so far. First, distributed training is utilized underneath. For one model, we have tens or hundreds of trainers in the cluster. Each of them generates and publishes streaming deltas concurrently. This is what our system looks like: distributed training, P2P distribution system, and single host serving. Next, as model size increases, a single host can no longer load the entire model. This is because even after quantization, the inference model size keeps increasing and it's reached a point where a single GPU host can no longer hold the large model due to its limited memory capacity. So we now partition the model across multiple serving hosts. This is what we refer to as distributed inference. Things get more interesting. You can now imagine we added another dimension to our distribution forest. We are not just distributing the training process, but also the inference system. The key challenge here is distribute the update unit to the right partition. This is crucial because if we send update to the wrong host, it will result in unused data, which is a waste of resources. So how do we achieve this? Basically, we pass the inference sharding plan to the publish job in the trainer. This way, the trainer has the knowledge on where this piece of data should be sent to, and we also create dedicated streaming channels for each inference partition within the P2P system to achieve efficient data distribution. Is this the end of complexity? Absolutely not. Let's consider another dimension introduced by the need for varied parts update. Different model parts can be updated at different cadence. For resource efficiency, we only update the highest valuable parts in terms of model freshness wins at the highest frequency. So effectively, there will be different data flows happens at different cadence. In this graph, you can see we have one data flow for sparse delta, and we have another one for item delta. Together, these different layers form a complex system, ensuring that our model remains fresh and responsive to real-time data, and ultimately, our users receive the best possible predictions. If you want to learn more about the details, please check out our blog post. Looking back, each evolution reduces training to serving latency, ensuring our models stay current and deliver more responsive results. With the complexity of our system in mind, from scaling training and serving to manage diverse updates, it's essential to address a central challenge here, balancing safety and reliability with the speed of the updates. We have a very clear trade-off: mean time to failure vs mean time to reward. One can either be extremely cautious when rolling out any change, or one can either roll out fast but also has ways to detect failures fast and roll back fast. As Infra team, we provide different approaches based on the nature of the updates, as shown in this graph. On the left side, this is what we call full model update. We always fully validate the model and validate key metrics like NE, and then deploy the model to production in multiple stages. This allows us to monitor the system behavior in a controlled manner and catch potential issues earlier. In the middle, we have critical delta updates. For dense delta, for example, which updates compute-heavy part of the model, we do lightweight validation and multi-stage rollout. On the right side is the fastest way of updates, streaming updates. For those updates, we do lightweight sanity check and push changes almost in real time. Meanwhile, we rely on continuous service health check to detect any issue and quickly revert to the last known good state if any bad delta got streamed. We have talked about how model freshness evolves in Meta and how we address its scaling and reliability challenges. At this point, I'd like to hand over to Vivek. He will walk us through our forward-looking strategies.
Thank you, Lujia and Xianzheng, for sharing your journey and the challenges we've had to overcome. It's a blast to work with you on it. Now let's talk a little bit about where we go from here. We've achieved some incredible results, but we're not done. First, we want to bring freshness down to seconds and test the boundaries of how far we can go. This is a brand new challenge for us, going beyond minutes, and we're looking forward to it. Second, model sizes are increasing. We expect that models are going to be an order of magnitude larger than they are today, exposing new limits in the infrastructure. Third, hardware heterogeneity. With the increased scale, we expect different types of hardware to come into our infrastructure. and that presents challenges for performance characteristics and the implications of it. Lastly, we want to take model development further. We want to introduce new model design paradigms in collaboration with ML engineers to fully unleash the power of infra latency reductions. It's a very exciting journey ahead, and we're looking forward to pushing the boundaries of what we can achieve. Thank you for listening.